Okay, so yeah, when given the two random variable, and then we subtract its own mean from each side. So if we think of the covariance of an x and x, and then we think of the expectation of x minus mu x and x also minus mu x. Okay. Okay, and so yeah, let me change it as y. So if we think of this covariance between x and y, and then we subtract its own mean. Yeah, and then multiply it, and then compute the expectation of it. Okay, so and also this measure is denoted by this formula, right? Yeah, so if we just distribute each of these terms from this product, and then we obtain this easily. And then using them, we can have this formula as well. So we now consider the variance of x plus y. And so we have the two variable of x plus y, and then its covariance is same as this variance. And then we think of this mu x minus mu y, because this part will be the mean of this part. And so we multiply them twice and then compute this expectation. And then you can easily compute or derive these formula. And so let's think about the meaning of it. When adding those two random variable, so here we think of a joint random variable, which means we collected a person's height and weight, right? And so they are originally having this form of a paired random variable, and so this is called an x and this is called an y. And then if we consider this a new random variable, summation of these two, and then their variance is actually the sum of those two parts as well as the covariance part times 2 times of their covariance part. So if covariance and the correlation has some commonalities, or they only have just one slight difference, where covariance x comma y divided by what? The variance of an x and variance of y. So this was our correlation coefficient, right? And this correlation was telling us whether the two variables are increasing together, or one increasing while the other decreasing. And so if they are increasing together, and then those two, sum of these two random variables, and their variance is not just the sum of each random variable, I mean the variance of these two random variables, but also they got some boost from their covariance part. Okay. And if we think of this minus, and then we can easily derive this as well. Okay, so in this first formula, if they are negatively correlated, then the covariance part will also be minus or negative value, right? So variance will always be positive, but covariance can be positive or negative, right? So it is, both cases are all possible. And so this guy can work as an additional, like an increase or decrease from the sum of the two separate variance parts. Okay, and yeah, let's use this example to compute this covariance of an x comma y. So yeah, you can think of it as a unnormalized covariance, and then you can imagine the patterns of these data points, whether they are increasing together or not. Yep, and yeah, we can obtain this part, this equation, and we can just plug this guys in, and then this part will be having this expectation value. So if x and y are maybe a person's height and weight, and then we just multiply them to produce this new random variable of x times y, and then we can consider their joint associated probability value, and we just compute the weighted sum of those x times y value. Yep, and then yeah, we can obtain this expectation part, and then yeah, we can also obtain the expectation of single variable of an x and y, and then yeah, we can compute this part. So yep, they roughly have some inverse relationship. So one is decreasing while the other is increasing. Yeah, and then if the two variables are independent, and then the covariance, yeah, the covariance will be what? Exactly 0. Yeah. So in this case, they do not have any patterns, whether they are increasing together or decreasing. Similar things. So yeah, they do not affect each other. So that's the physical meaning of this covariance. And I mean, yeah, that's the meaning of this independence, if they do not affect each other. And in that case, the covariance term will always be 0. And in order to prove this, yeah, the covariance part is the expectation of x times y minus expectation of an x, expectation of y. And so if they are 0, then they should be equal. Yep, and so yeah, we can compute this guy into this, but this joint probability or joint probability function can be decomposed into these two parts, the first one and the second one. And then yeah, these summations will be separated out into these two parts of expectation of an x and y separately. So yeah. And then in this part, yeah, this has a little bit of a general form where we have n random variable, but if we think of just the two random variable and their sum, because we are considering the sum of these two, then yeah, we can recall or remember what we learned here. So in this case, yeah, it's a summation of these separate random variables variable, and also this covariance part, but this covariance part will be 0, and so yeah, it will be always decomposed into the sum of separate random variables variance. Any questions so far? Okay, that's it for chapter 4, and then let's move on to chapter 5. Okay, so in this chapter, yeah, we will study a special random variable, which means a particular random variable has a special, its own probability density function or distribution function. And the first one is a Bernoulli random variable. It's just like a coin flip, but yeah, so we have only like two possible elementary events or individual events. And then each event will be enumerated as a random variable like 0 and 1. And we are more interested in the event that corresponds to the random variable of the value of 1. And then, yeah, among these two different events, we can consider their probability distribution, or P versus 1 minus p. Okay? So this is a Bernoulli random variable. Okay, and then in this random variable, as we saw maybe in the last class, if we think of this expectation of an x, then yeah, based on this expectation formula, we can obtain the probability value itself. Okay. And then using this Bernoulli random variable, yeah, we can perform multiple trials of sampling or obtaining those yeah, Bernoulli random variable values. So we do this sampling process on this Bernoulli random variable case using multiple times. Okay, so that is called this binomial random variable, and yeah, specifically in this case, when doing this multiple trials, we actually count the number of this event that we are more interested in. Yeah, so that is called this binomial random variable, and they have the parameters as n and p, and this n is the total number of trials that we do, and then p is the probability of this individual event within a single trial. And yeah, when this value is I, which means we observed I number of this event out of n event, and then what is the probability? And in this case, yeah, p happened I times, and 1 minus p happened n minus I times. And then we can have a possibly multiple different orders of this p events on this part, and I number of events and n minus I number of events, and that number is represented by this, yeah. So this is a NCI, right? Okay. So this is what we learned probably in high school. And then, yeah, this is the probability distribution of a binomial random variable for a particular parameter value. So if n was 10 and 0.5 was the probability of a particular event that we are interested in, assigned with this random variable value as 1. Okay, in this case, yeah, roughly every time we have the probability of 0.5, and then we do it 10 times, and so in terms of the number of this events occurring, approximately we will have five events happening. Right? The number of this event happening will be 5. And so yeah, we have roughly 5 as our mean value, and then also it has the mode in the same part, and then the distribution looks like this. Yeah, and then if p is 0.6 or 0.3, then it will be biased towards the 3 and 6, which are also our mean value. Okay, and then the distribution has this. Okay, and then the mean and the variance of this binomial random variable can be computed by using this function of random variable. So since we assigned the random variable with Bernoulli random variable value as 1 in case that event of an interest happened. So if we just sum those random variable Bernoulli random variable values of these n trials, and then that will be just that will mean the count or the number of such events happening. Okay, and then we know what RP, or its distribution. So xi, xi is 0 and 1. Then we have it's a probability distribution function. So it's a p and minus p. And then we consider this a summation of this Bernoulli random variable. Okay, and then expectation of, let's first think of is expectation and the variance of Bernoulli random variable, which is xi. And then, the expectation of xi is p, and this variance can be computed in this formula. So, we utilized this guy, xi squared minus expectation squared. And this guy was computed as p, and it will be p squared. And then what about this part? So we consider the function of random variable in this case, and its probability value will be 1 minus p and p. And then what is the function output of xi squared? It will be 0 squared and 1 squared, right? And then we just compute the weighted average among those possible value of xi squared. And then it's p times 1 and 1 minus p times 0. And so it will be just p, right? And so if we factor it out, and then we have p and p times 1 minus p. Okay, that was a mean and the variance of Bernoulli random variable. And then in the case of, they are the same thing. So they are duplicate one. And then in the case of binomial random variable, which are the summation of those Bernoulli random variable, then it is just expectation of x1, expectation of x2, expectation of xn, where I is the trial index. So this is the first trial's outcome and the second trial's outcome, and so on. And so each entry has the expectation as p, and then altogether it will be n times p. And in the case of variance, and then we can write it as the sum of these variance. And how can we write this variance as the sum of this variance of an xi? Can anyone tell me the reason? So why are these true? Why is this equation true? So if we consider just two random variable, x1 and x2. Let's suppose we did 2 times of this Bernoulli random variable trial, and it's variance of x1 plus x2. So in this case, as we saw the equation earlier in the last part of the previous slide, it is variance of an x1 plus variance of an x2 plus variance of an x1 comma x2, right? And then this part should be 0. And why is it so? So they are independent trials, right? So each trial of coin flipping doesn't affect each other. So this part is 0. So expanding them with the multiple entries, so it will be shown as just the sum of the variance of each individual random variable. And so this guy was p times 1 minus p, and then yeah, it's just yeah, multiplied by n. Okay, then the next one is Poisson random variable. Yeah, so in this case, yeah, let's try to understand the meaning or the situation considered when discussing this Poisson random variable. So we think of some time period, okay? So we have some timeline that is just having this continuous axis, okay? So this is maybe 5:45 p.m. maybe 5:45, not 54 and 5:55 and 5:56 and so on, right? So these are lying in this continuous time domain, right? And then yeah, we consider really small range or small region, okay? And let's consider some event, yeah, which is like a Bernoulli event, like a some event happened within such a small period of time, and that probability is called a p. Okay, so a particular event happened. Yeah, the probability of a particular event within very small region of this time is called a p. And then we do it. We do this kind of trial multiple times, and yeah, that number of trials will be n. So again, yeah, suppose suppose some customer visits some bank, okay, or some convenience store, and then let's consider our time unit as just 1 minute, okay, which is a really small time period. And then let's consider the average number of people visiting within such a short amount of time. Okay, so that number is called this p. Okay, and then we consider n trials, which means we consider maybe an hour, where n is 60. Okay, one time unit is 1 minute in this case, and then we consider 60 times of it. Yeah, and then what will be the average number of people visiting within 60 minutes? Okay. And it will be n times p. Right? So it is almost similar to binomial random variable. Okay? So we consider the probability of a particular event happening within really small amount of time. And that will be really small probability value, and that is called this p. And then we consider really long time range. Okay, so in this case, the average number of people that visits within 60 minutes will be n times p, which is just like the mean value or expectation value of a binomial random variable. Okay, here one different situation from binomial random variable is that this p is really small value, and also n is really large value. Okay. So p goes to 0 means we can consider maybe even a single second as our unit time. Okay, just a second. And within a second, how many people can we expect to visit a convenience store? It will be close to 0, or this probability will always almost 0. But in order to consider like a 60 minutes, 60 minutes is fixed. And so if we consider 1 second as our unit time, and then 60 minutes will correspond to n of this 3600. So we consider this kind of situation. Okay? So they are competing with each other, and n times p. Okay, so the average number of people visiting the convenience store within an hour. Okay, within an hour, that will be some number that are not too small or not too large. Okay? So we consider this kind of this kind of a situation, and in this situation we consider the number of people that actually visited this convenience store within 60 minutes of time, and that number can be 0 if we get really unlucky, and it can be infinite numbers, right? So there's no limit or upper bound about the possible value of our random variable. Okay? So in the case of binomial random variable, n was fixed, right? N was fixed, and so the maximum possible value in the binomial random variable was n, right? So the maximum count will be n. But in this Poisson random variable, it can be infinitely large value. Okay, and in this case, it has this probability mass function. Okay, and then here we see this lambda as a parameter value, and this lambda is n times p, which is the average number of customers visiting our convenience store. And then, let's think about this. Let's view this probability mass function a little bit more closely. And then, this is the number of people or customers, and if lambda is given as our parameter, so lambda is fixed parameter. So just like a binomial random variable where we have a fixed n and p value. So here, p and n are also fixed, and thus lambda is also fixed. And so some number to the power of an I. So I is our random variable value, and this part is a constant. Okay, and this part is also growing, but as I gets larger and larger, so this value will be just a factorial. Okay? All the product of n I or I minus 1 all the way to 1. Okay, so this guy goes to infinity if I gets larger and larger, and also this part will also go to infinity as well if lambda is more than 1. Okay, so if lambda is 4, okay, then we should have the expectation value as 4, right? And then it has this kind of distribution. And we do not prove this, but by using something called the moment generating function, we can obtain or compute the mean and the variance of this Poisson random variable, and that value is all lambda. Okay, so the mean value is lambda is obvious, although we do not know why the probability mass function should look like that complicated form, right? But let's just take it as it is. So there is no kind of proof or something like this. So someone just found that particular expression, and in that case, there this expectation or the mean value and the variance will all be lambda. So that means if lambda gets larger, and lambda is the average number of customers, but at the same time, if it follows Poisson distribution, this variance will also get larger and larger. Any questions? Okay, let's look at some example. So here, the average number of an accident occurring weekly on a particular stretch of a highway equals 3, which means lambda is 3. And if it follows the Poisson random variable or Poisson distribution, and then we have to calculate the probability that there is at least one accident per this week. Okay, and then we have to consider the probability of this case. And there are infinitely many possible cases where x being 1, 2, and maybe infinite value. And then it can be conveniently computed by 1 minus this guy, because this is the only remaining case. And we can just plug this 0 into the probability mass function that we learned here. Okay, so lambda was lambda was 3 in this case, and then we can easily plug this value 0, and we can compute this probability. And let's look at the next example. Suppose the probability that an item produced by a certain machine will be defective is 0.1. Okay, and then the probability that a sample of 10 times will contain at most one defective item, which means out of 10 items, either 0 defective item or no defective item, or just one defective item. Okay, and then this is actually a binomial random variable, so it follows the binomial random variable. Because we are, the number of trials is 10, and then each trial, the probability of this event happening will be just 0.1. So we can compute the probability of these cases by using binomial random variable probability function. And so, in case of 0 events happening, it can be computed by this, and then you can also compute the probability corresponding to this case. And then altogether, the probability is computed as 0.73. Okay, and then here, let's just consider it as a Poisson random variable. So this is not exactly a Poisson random variable. It's a binomial random variable, but as I mentioned about the relationship between Poisson random variable and also binomial random variable, so they are kind of Poisson is a kind of approximate version of this binomial random variable. So so if this was really large, okay, if this was really large and correspondingly this was really small, okay, so that value of n goes really large and this value goes to really small value with the same velocity, and then np, or the average number of these events happening, will remain the same, remain as the fixed value. And let's just consider such situation. I mean, even though 10 is not that big, but let's just do the Poisson approximation anyways. Then we can compute the corresponding Poisson random variable and its probability corresponding to those two events by following the formula of this Poisson random variable. And it has this probability. And so those two probability values are very close to each other. So that verifies that the Poisson random variable is nicely approximate, or is quite close to our binomial random variable. Okay, and then the next one is a hypergeometric random variable. So it's almost the same as binomial random variable, but the sampling is done without replacement, which means, so let's consider this situation. So we have n acceptable battery and m defective battery. So in total, in our jar or in our pocket, we have n plus m number of batteries, and in this case we want to sample, or we want to extract out lowercase n number of batteries, and then what will be the count of what will be the count of, let's see, so do we consider the defective battery or acceptable battery? Okay, so I samples were selected or chosen from n, so we are thinking of this acceptable battery as the event of our interest. Okay, and so we consider the count of acceptable battery when picking up small letter or lowercase n number of batteries out of these n plus m total batteries. So in this case, the possible choices of picking up I batteries from this n acceptable batteries. So out of n, we have to choose I batteries, and out of m, we have to choose correspondingly small n minus I batteries. Okay, so this case is NCI, which is all the possible different cases of picking up I different acceptable batteries out of n. And then we have to pick up n minus I battery. It should be large n. And out of m, we have to pick up n minus I defective battery correspondingly. And this is all the possible cases, okay, of choosing I number of acceptable batteries. And then it should be divided by the total number of possible cases of picking up just n batteries out of n plus m. So that way, n plus m c n is the total number of cases. So the ratio between these two will be the probability. Okay? So the probability corresponding to this event of seeing I number of acceptable batteries. Any questions so far? So in this case, let's look at the possible values of this I. So I can be 0, and the maximum value will be the minimum number between large n plus small n. So that means, so suppose we have maybe 5 acceptable battery and maybe 8 defective battery. And then the number of acceptable battery that we can pick up can be, the maximum value will be this n. So for example, suppose n was 3. So in this case, what is the possible value of an I? It will be 0, 1, 2, 3. But what about n being 7? So in this case, we are selecting 7 batteries out of 13 batteries in total. In this case, this I can be 0, 1, 2, 3, 4, 5, which means we have to, we can pick up to 5 acceptable batteries, because that is the total number of acceptable batteries. So that's what this means. Okay, so this is a hypergeometric random variable. And this one is similar to a binomial random variable. So in the case of binomial random variable, we treated, or we thought of each trial separately, right? But this binomial random variable case can be also considered as, so suppose we do 10 trials, and then the probability of picking up a maybe acceptable battery as maybe 3 over 10. So in this case, we can think of our trial as having 3 acceptable battery and 7 defective battery out of these 10. Yeah. And then we pick up 1 battery from there, and then we replace it in the jar, which means we put the selected one or selected battery into the back into the jar. So that 3,7, that number will always remain as fixed values or the same value, and thus each trial will have the same situation. So that way, this binomial random variable is just the same trials with replacement, which means we put the sampled one back to the jar. But in this hypergeometry one, we do not put it back to the jar. That's the only difference. So those trials will be dependent from all the previous events, and and then we can also consider the probability. Yeah, so this is the probability at the very first or the initial trial. So out of n plus m, so we have n acceptable battery. So this is the probability of picking up the acceptable battery at the very first trial. So you can prove the expectation or the mean and the variance of these hypergeometric random variable case, and it's almost the same as the binomial random variable case. So the mean value will be exactly the same, and then the variable, the variance will have this kind of form. So it's a little bit tricky to prove, but let's try to understand this one has some similarities with binomial random variable. So in the case of binomial random variable, the only difference is whether we do the trials with or without replacement. So in this case, if n plus m is really larger than the number of samples or number of trials. Okay, so in this case, whether doing the trials without or with replacement will not affect much, right? So in this case, this one is really big and this one is really small, if we consider this situation. And so this part will be close to 0, and thus this part will be 1, and thus we obtain np times 1 minus p, which is the same variance as a binomial random variable. Okay, and in this case, so we have a 20 components in our jar, and then we have to pick up the 6 components, and then the total number of possible cases will be picking up a different combinations of 6 components out of 20. So in the denominator we have this, and then here we consider x being greater than or equal to 4. So so we have 4, 5, 6 as the possible value, because we have in total 6 elements as the something like acceptable battery corresponding to the event of an interest. And then yeah, we can just sum all the possible cases, and then the ratio of these counts of the events of an interest versus the total number of cases. That will be the probability value in this case. Okay, then the next one is a uniform random variable, and the uniform random variable is a really easy one. So we are given a particular interval, and the probability within that interval will always be the same. So if alpha was 3 and beta was 5, and then we have probability, equal probability within this range. Okay, and then since we have to have 1 as the area under this curve, or this guy should be 1, so that this guy is a density function. This guy can be a density function. So what should be the height in this case? So it's a rectangle, and it's 2, and this one should be 1 over 2. Okay, so that 1 over 2 is represented by this equation. Okay, and then we can consider its mean value, and mean value can be computed by plugging or multiplying this probability value by with the variable x, and then we can compute this integral, and we can just compute it so that we can obtain this expectation value. And then what about the variance? What about the variance? So if alpha was 3, alpha and beta was 3, 5, and in this case we have to compute the multiplication product of this fixed or constant probability density value times x squared, and integrating it over this range will be the expectation of x squared. So in this manner we can compute this guy, and if we set alpha and beta and this guy as beta minus alpha, and then we can obtain this expression, and minus this guy is the expectation of an x squared, and that will become this, and then after evaluating it, we obtain this as our variance value. Okay, and then the next one is Gaussian random variable. So I believe you guys are memorizing this Gaussian random variable density function. So Gaussian random variable is the same as the normal random variable, and it has the notation of this curly letter of an n, and the parameter is mu, or the mean value, and the variance value. And using those two parameters, the Gaussian random variable will be determined. And we can compute this mean and variance, and it requires some special formula to obtain its integral. But overall, the idea is, we put we compute the expectation of x minus mu. In this case, we plug this guy into here, and then we put this constant out of this integral, and then we obtain this, and then we do some transformation of this guy with this y. Then you guys can use this kind of transformation into this this integral. So we obtain this dy, and 1 over sigma and dx, right? So instead of dx, yeah, we put this guy here, right? And then this guy is, yeah, coming out of this integral. Then we obtain this. Then here, yeah, we can see this value as 0 because this guy is what? This guy is what kind of function? Yeah, among the even function or odd function, this one is even function, right? So it's yeah, if we mirror it along the y-axis, and then we will obtain the same function. And this guy is odd function, right? So it's mirrored with respect to the origin, and then we will obtain the same, yep, yeah, same function function shape. And then altogether, if we integrate those product of even function and odd function, then the product of even and odd functions will be odd function. Yeah. So odd function integral over all the regions of this odd function will be 0, and thus it will be 0, which means the of an expectation of an x will be u. And yeah, you can also do the similar thing to derive the variance of this Gaussian random variable. Okay, so yeah, let's stop here today. And yeah, again, sorry for being late. And yeah, I'll see you guys next time on Thursday. 네.
무한원에서는 시도 횟수가 무한하다는 기본 하이스쿨
네.
i가 이제 무한대까지 간다고 그게 수행 횟수가 무한대라고 봤지. 그러면 근데 실제 상황에서는 무한대는 아니잖아요.
네.
실제 상황에서는 그냥 거기까지만.
네. 맞아요. 그러니까 실제 상황에서는 이게 그러니까 바이노미얼이랑 같이 이렇게 비교해서 생각을 하기에 좀 뭔가 직관적이니까 이제 그렇게 생각을 한 건데, 이제 보통은 어떻게 생각하냐면 그냥 파라미터가 하나 있는 거고요. 그 하나는 뭐냐면 우리는 그냥 1시간이면 1시간, 그러니까 뭐 어느 정도 시간 그게 있는 거예요. 우리가 생각하는 어떤 기준이 되는 시간의 그 길이가 있고, 이게 1시간이면 1시간이라 그러면 그 1시간 내에 어쨌건 그 고객이 뭐 이렇게 방문하는 그 고객의 숫자라든가, 아니면 어떤 사건이 그 1시간이면 1시간 내에 일어나는 숫자, 그게 뭔가 평균적인 그 숫자가 주어지고요. 그 다음에 이제 어떤 특정한 디스트리뷰션을 따랐을 때 그거에 해당하는 확률 분포가 아까 예제가 뭐 하나밖에 없었지만 이제 이렇게 생긴 거죠.
그 상황에서 람다가 먼저 주어진 거예요.
우리는 n과 p 이게 주어진 다음에 그 다음에 람다를 생각하는데, 일반적으로는 그냥 람다만 줘요.
그래서 p를 구하는.
그리고 이제 그거를 이제 바이노미얼이랑 생각을 하면, 그러니까 이거는 뭐 이런 이상한 펑션, 이런 이제 디스트리뷰션을 가지는데 이건 뭐 뭔지도 모르겠고 뭐 그렇잖아요. 근데 이제 이게 이제 어떤 조금 그 의미를 가지느냐, 우리가 바이노미얼은 뭔지 아니까 그 바이노미얼이랑 거의 이제 흡사한 형태의 그거고, 바이노미얼에서 이제 n을 이렇게 키우고 이제 한 번 일어날 때 확률은 이제 굉장히 낮춤으로써 평균적인 일어난 횟수를 이제 우리가 이제 우리한테 주어진 람다랑 이제 똑같이 맞출 때 그때 상황이랑 이게 거의 일치한다는 거예요. 네.